with aqueous solutions in water, there's two types of dissolution or dissolving. The first type we'll talk about happens when you have an ionic salt, such as NaCl. And NaCl, even though we know it as table salt, is not the only salt. There's many different salts. And what a salt is, by definition, is the ionic, or a soluble ionic compound is considered a salt. So any type, whether it be magnesium sulfate or sodium carbonate, those are all different salts. So in this case, in any of their cases, they have a positive and a negative ion. The positive ion is a cation, and the negative ion is an anion, which we know about. And the way they dissolve when they are entered into the medium, into the solvent of water, is the water molecules, because of their polarity, will have a charge attraction to each of the cation and anion of the ionic salt. So if you have sodium, which is in purple right here, okay, yep, which is in purple right there. So sodium is going to be attacked, and you see it's kind of surrounded by the red oxygen atom, right? And that makes perfect sense because we know from the last slide that oxygen is partially negative. It has this partial negativity to it based on the increase in electron density because of its polarity, or it's a higher electronegativity than hydrogen. So what will happen over time is if you put a salt crystal into water, even if you don't really excite the water at all by stirring it around makes it happen faster, but or changing the temperature or the pressure. But even if you just leave it there, what will happen is the negatively charged oxygens will kind of gang up and attack the positively charged sodium ions, and thus ripping them away from the rest of the salt crystal. So that's how dissolution happens for ionic salt, for soluble ionic salts. Some of you are thinking, oh, if you say soluble ionic salts, there must be insoluble ionic salts. And you're totally right, and we'll learn about those towards the middle of the class. Now, similarly, you have other water molecules in the solution, and those that will attack the negative anion. So you have the positive cations attacked by the oxygens of water, and the negative anion that's in green is attacked by the positive hydrogens because they're a positive negative interaction, and they will attack and they will solubilize the negative ions. So if you take this and over time, over the course of a couple of seconds, you have millions of water molecules attacking millions of, or less millions, of sodium chloride, thus ripping it apart into its ionic components. Now this gives the entire solution a charge because of its positive and negative ions. That charge gives it the ability to be conductive and to conduct electricity through it. So that's why we call this kind of solution, where you have the dissolution of ionic salts, an electrolytic solution or an electrolyte, because it has the ability to conduct electricity through it. So when you think of electrolyte, I'm sure you think about what drink? Gatorade, exactly, right. So what electrolytes mean in Gatorade doesn't mean if you drink it, you're going to get electrically, well, it does mean you're going to electrically charged, but you're not going to get zapped or anything. What that means is it's full of ions. That's literally it. And some of these ions are very important, essential ions for our muscles to move and to exert energy, such as magnesium, calcium especially. You have sodium, obviously, chlorine, a little bit, potassium, really a lot of the group 1A and 2As. And iron is in there too. Cobalt, not really. If you take multivitamins, you'll have some of the other ones like selenium, cobalt, copper, nickel. Those are ones that are trace elements that are in our body that are still important for our metabolic processes. Zinc, of course, zinc is very important. Okay, cool. So that's one type. That's where we have the electrolytic solution. Then we have another type of dissolution in water that is not electrolytic, which is called a non-electrolyte, but it still dissolves in water. An example of this is sugar. There are different types of sugars, but we'll just talk about generally, and they all behave the same in water. This is a sugar molecule. Now, sugars are an organic molecule, meaning they're based in carbon, and they have carbon, oxygen, and hydrogen, and they are polar. So they are polar just like water, but they can't be split apart into ionic components. like sodium chloride can. So water is going to do what it knows best, and it's going to bond by an electrostatic interaction, and the positive charges of the hydrogen will bond to the partial negative charges of the sugar, while the partial negative charges of the water will bond to the partial positive charges of the sugar. So it'll kind of just make this polar interaction. But it won't rip apart the individual sugar molecules, but it will rip apart the sugar from its crystal. Let's say you put a cube of sugar into water and you stir it around a little bit, it's not going to be a cube anymore. It's going to be ripped apart into its molecular components, but not ionic components, because the sugar molecule, it has a ring. It's basically a ring with carbons and oxygens in it. It doesn't really split apart into its ionic components. So thus not being split into its ionic components, that means it's not going to have a net charge at the end of the day. So no net charge in the solution means you're not going to have electrical conductivity. You have electrical conductivity when you have a salt solution, not a sugar solution, because you're in the salt solution, you're having a physical breaking apart into ionic components, giving a plus and a minus charge. With that charge gives it an easier electrical conductivity. And these are called electrolytes. And then you have things like sugars that are non-electrolytes. So the definition of a strong electrolyte, even with splitting electrolytes and non-electrolytes, further branching off of different types of electrolytes. So those being strong and weak. So the strong electrolytes are these strongly soluble ionic salts and also strong acids. Then there are weak electrolytes, where out of 100 molecules, maybe 4 of them break apart, and 96 of them stay as their original molecule. They don't break apart. Weak acids and weak bases that do this. And here it says weak acids and solutions conduct electricity. Yeah, we know that. But they conduct electricity, and you can imagine since they're weak, they do it very weakly. A question that you should have, how the hell do you determine a weak acid and a weak base, and a strong acid and a strong base? So I want to know the difference, right? Hickel, Hibber, High, Hino, Hiklo, Hiso. Weird, right? Okay, so I'll say it slowly. Hickel, HCl. Hibber, HBr. High, hydroiodic acid. Hino, it's not perfect, HNO3. Hiklo, there's actually 2 Hiklos, so it's not perfect. Hiklo is HClO4 and HClO3, and Hiso, which is H2SO4, which is the strongest one. And they're not in strong to weak order by any means, but this is a list of all of the very common strong acids. What about the weak acids? Is there an acronym for that? The answer is no. There's no acronym. But if you know the strong ones, by process of elimination, you know the weak ones. So anything that's not on this list, this Hickel, Hibber, High, Hino, Hiklo, Hiso, is a weak acid. Then you have strong bases. There's no cool saying for strong bases, unfortunately. And this is written in textbooks that it's the group 1A, 2A hydroxides, for the most part, the ones that are soluble. Some of them are not the most soluble, such as magnesium hydroxide and calcium hydroxide. They're kind of like very mildly soluble, but the ones that are considered to be strong bases. And then for weak bases, it's basically everything else. Get it? Basically. But it's basically everything else that's not on this list. And there's one such as the other hydroxides. Like if you have transition metal hydroxides, those are going to be weak. But there's one that you should know, and that's ammonia. So I'll write that down. So I write everything else hydroxide plus NH3, which is ammonia. There's also other ones, like in organic chemistry, a lot we use like calcium carbonate, magnesium carbonate. Those are really weak bases that are in antacids. So like calcium carbonate is in a lot of antacids. So yeah, non-electrolytes are going to be anything sugar. It's a complex structure that you can't break apart into ions based on the ions you know. So based on everything you learned from chapter 3 and 4, you should know that you have your polyatomic ions, you have your cations, and you have your anions. In everything, in the weak electrolytes and the strong electrolytes, you can clearly pick out your ions. So even for this weak electrolyte here, this H+, it's an H in front of it, probably an acid, and this C2H3O What ion is that? Acetate.
In short, non-electrolytes are going to be larger structures, usually organic, that you cannot break apart into its constituent ions like you can for strong and weak electrolytes.